Okay, this is the lab part of the divider and voltage drops tutorial. What I've got is I've tabulated a whole bunch of values here. So for example, I've taken RB here and just set a whole lot of different values on the decade box when we run through this. Now the 18K resistor is actually a resistor within the circuit. That's not going to change, that's going to be fixed throughout. So the only thing that's going to change are these RB values. So as we change these values, then obviously the voltage drops across both of them are going to change. And I've used the voltage divider formulas here plus Ohm's law to get all of this all ready to go. So we've got all of these done already. Now wiring this circuit up, we should see that these calculated values actually match the measured values. If the measured values are close to these, then we know that the voltage divider formula is good, Ohm's law is good, and that everything's as it should be. If for some reason we don't get the same values, then the most likely scenario is that we've connected up the circuit incorrectly. So you can do this simple circuit yourself. It's just basically one resistor and a decade box, so it's very easy to set up. All you need here in the circuit is I put an inline ammeter. So basically just using a multimeter. You could use a multimeter and set it to current reading. I've used a single voltage voltmeter here, and I've got leads so I can drop between the fixed resistor and drop it between the decade box, so that I can show you the voltage drops as we go through this. Obviously the whole thing's running on a fixed 12 volts. So let's have a look at the bits and pieces. So what we've got is we've got the decade box, which is for the resistor values here. I've already got this set to 18,000 just to begin this. There is the voltmeter. We're also using an AVO ammeter. So this, well, basically this is just an AVO meter, but I've set this onto the current setting at its lowest resolution. So this is now set. Oh, hang on, just make sure that's set at the lowest resolution. So that's good. What else have we got? Okay, here's the actual circuit on the breadboard. So there's really nothing much going on here. So I've connected up the decade box to so it's in series with this fixed resistor here. So this is the single, well, the only component really on the breadboard. Everything else is just connected wires. So you've got wires connected to the ammeter, which is in line. Then you've got the decade box connected here, and the voltmeter. I'm using these two leads here like so. So we're going to put these leads in. Now when I swap between the resistors, all I have to do is pick them both out, and then we get the voltage across both resistors like this. So I've done this just to make it easy for you to see. Instead of using 2 voltmeters, it's much nicer to see that we're actually moving these across the resistor, so you can actually see the change in the voltmeter and then read the different voltage drops. So this is already running now. I've got this running at 12 volts. The actual power supply is on, which is over there. So the power supply is actually on now. So what I'm going to do is basically just turn on the voltmeter. Okay, so the voltmeter is on. Now let's have a look at what we should be getting. So we'll have a look at our results here. So for 18, we set RB, this column, we set RB to 18 where the arrow is there. Now at 18, obviously both resistors are the same value, so 12 joules per coulomb, we're going to drop 6 joules per coulomb across each of those. So that should show 6 volts on both of those. And then when we look at the ammeter, we should see that the current is if you do Ohm's law with 12, if you do Ohm's law using those using 218, you get 36,000. You get 12 divided by 36,000 gives you 0.33 recurring. So we should see that the ammeter shows 0.3 milliamps. So let's just check that first one then. Okay, so the volt. So we've actually got the voltmeter dropped across one of those already, and you can see it's showing exactly 6 volts. So let's just move these over to the other resistor. I don't know which one it is, but it's the other one. And that's showing 6 volts as well. I mean, you know, give or take a couple of hundredths of a volt. So that's good. That shows that this is probably connected up correctly. So let's go through some of the others now, just to prove to ourselves that these numbers actually follow the actual measured. Actually, I'm going to swap those round. Not that it really matters, but I don't like to see the minus sign there. So yeah, so there's a. I'm going to have those like that. So let's have a look at maybe one of the others now. So why don't we just go, we're at 18,000 for RB, let's just set it to 36,000, which is the bottom one there. When we set it to 36,000, we should see the voltage across VA go from 6 volts down to 4 volts, and then the voltage across VB, which is the decade box, that we'll know which one's the decade box now, because that'll show 8 volts. So as soon as which one says 8 volts, we'll know it's the one that's dropped across the decade box. And when we check the current, it should show 0.2 milliamps. We didn't check the current on the last one, but we'll do that now. Just before we go to let's just check the current. So we're going to stay with where we were. We're on 18,000. And 18,000 on both resistors, giving us 6 volts across both. So from that should give us, looking at this, 0.3 milliamps. Let's just check that we've got that. So here's the ammeter. Right, so now I'll show you with my finger because it might be difficult to see this, but where my finger is now, that's about 3.3 milliamps. So if we see that needle flick close to where my finger is at the moment, that should tell us. So I'm just going to switch that on. Yeah, and I can tell you, looking at it, I can see it quite clearly. That's 0.33 milliamps. So that's absolutely spot on. So that's good. So let's go now to 36,000, which was the bottom one there. So now we're going to go to 36,000. So we'll set the decade box to 36,000 now. Okay, so we've got 36,000. So let's have a look what we've tabulated that. So for 36,000 we should say 4 and 8. So the voltage across the fixed 18k resistor should show 4 volts. So let's see, and the other one should show 8. Right, so now we know that the leads currently are dropped across the decade box, because look, it's 8 volts. So I would say now we can move over, have a look at the other, and the fixed resistor is showing 4 volts, which is exactly what we've actually calculated. So that's good, that actually proves it. Let's go back and just show you that again. 8 volts. And now let's have a look at what the current's supposed to be. So the current's supposed to be 0.2 milliamps. Now I'll just show you that with my finger. 0.2 is where my finger is there now. So that's, if you see that needle should move to about where my finger is. So keep an eye. It'll drop down. I'll just show you where 0.2 is again. That's there. Just have a look at the needle again. Okay, so that's showing 0.2324. So that's pretty close. Now let's look at another one just to double check. Okay, we'll go with in the actual last video we showed 6,000 and 18,000. So let's do that one now, which is that one in the middle there. You can say 6,000. If we add 6,000 to 18,000, we get the total resistance, which is 24,000. We should see 9 volts across the fixed resistor and 3 volts across the decade box, and the current should show 0.5 milliamps. So let's just check that. So we're going to set that to 6,000 now. So we just zero that. So that's 0, and that's showing 6,000 now. So let's see what the voltmeter says. That's showing more or less 3 volts. What was the other one? The other one should show 9. So if we move these leads over, we should see 9 appear on that voltmeter. There you go, nearest damn it, 9 volts. So we've confirmed that all of these numbers here so far are correct, and obviously they're going to be correct for the rest of them as well. Let's just check the current. Right, the current is 0.5 milliamps. So I'll just show you that with my finger. That needle should now go to where my finger is now. That needle should go right up to there. So the needle's there at the moment. You should be able to see that. If the current shows 0.5 milliamps, the needle needs to go there, as with our calculations. So that's check that. Yeah, you can see. Let me press that again so you can see. There you go. That's exactly on 0.5 milliamps. So there you go. So all of these numbers actually confirm all of our calculations. The experimental numbers are identical. So there we go. We know that these voltage dividers work. We know that Ohm's law is good. Everything works. Everything is as it should be. So this is a good experiment. If you do this, you get a nice feeling, because you can see, you get good confirmation when you actually do the real thing. And it's really nice to see the numbers actually match up when you do an experiment. Although it might seem a very simple, well, it is. It's a very simple circuit. But don't let that put you off. Definitely give it a go, because when you start, if you measure, like I say, the voltage drops across the 2 resistance, and then actually calculate the current, calculate the voltages, then when these numbers match up, you'll actually learn a lot by just doing this. I mean, it's all very well using software packages to emulate things, but you really don't get, it doesn't really sink in as well as when you actually physically build it and do it. I mean, that's really simple build. That'll take you 5 minutes to build one of these. You don't need to use all these bits and pieces I'm using. You can get a really cheap multimeter. You don't need to use a decade box. You could just line up a whole bunch of resistors. I mean, I've only used a decade box because it's easier. But you could just line up a whole bunch of resistors along the breadboard there, and just emulate this experiment and do it. I mean, even if you've got a really cheap multimeter, it'll still be within 1/100th or so. It'll still be reasonably accurate. So give it a go. Anyway, on the next tutorial, I'm going to go over Thevenin's theorem. That's a nice thing. A nice strategy to use when you want to join up different modules, if you like. You want to join up different bits of circuits so that they match. It's sort of, we're heading towards impedance matching here. So before we get into discussing a lot about impedance matching, we go over Thevenin's theorem first. Now, what we've done in these last 2 videos about voltage dividers and voltage drops leads really nicely into Thevenin's theorem, and it'll make more sense if you now understand voltage dividers, and if you've done this experiment as well. Okay, thanks very much.